Okay, so I talked about in the last lecture the importance of being able to solve either Poisson's or Laplace's equation in order to find the electric field, but we haven't really done a lot of examples of how to do that. So let's start with the simplest case. We're going to learn how to solve Laplace's equation in one dimension. So in one dimension, Laplace's equation simplifies a little bit. And it ends up looking like this, okay? So again, we only got one dimension, so we're gonna call that the x direction. And I want you guys to note, in this case, and it's just kind of a mathy thing, okay? Now we have a total derivative, not a partial derivative. And the reason for that is because there is only one dimension or variable that the potential can now depend on. And that is, of course, x, okay? So this is what we call a second order differential equation. Okay. And, you know, I'm not a math professor. There's different techniques for solving differential equations, but in physics, I feel like we all often use the old guess and check, okay? Which is, what's called the DE, it's not an ordinary. Educated guess and check, right? You're not just randomly guessing any equation, you already kind of have an idea. In this case, you know, right, that the second derivative of some function with respect to x is 0. Okay, so that should tell you that one equation where the second derivative with respect to x is 0 is a first order polynomial, also known as the equation for a line, right? So that's my guess, and I'm going to go ahead and just check that. Indeed, if I take one derivative with respect to x, I get m, and then if I take a derivative of that function with respect to x again, I get 0. Okay, so it seems to satisfy my original differential equation. That's good, okay. But in order to get an actual full solution, I need to figure out what m and x are, okay? So this is what we might call a general solution. Let me write this over here. This would be the general solution, which means it works generally for many cases, but to get a specific solution rather than a general one, we need to figure out what m and b are, okay? So in order to do that, we need some boundary conditions, okay? So this is not so different than regular differential equations. I'm sure you guys know in order to solve a first order differential equation, I need one boundary condition, or often called an initial value. To solve a second order differential equation, I need two boundary conditions, okay? So the order of the differential equation basically tells me how many boundary conditions I need, okay? So in this case, I've got some choices. I can know if I could either know the potential at two positions x that could bound my problem, or I could know m, which is the same thing as taking the derivative with respect to x, and v at one position. Okay, that would be enough also to bound my problem. Okay, so let's just do an example here. And we're going to apply this to a real system, which will be our 2-plate capacitor. Okay, so we got a 2-plate capacitor here. I'm going to draw it from the side. Okay, now maybe I'll make that a little more interesting. We'll do something like that. Okay. And I'll do another one. Like that. Cheat a little bit here, get rid of these guys so it looks like a surface. Just bigger. Okay, loving the electronic pens. Okay, so we got 2 plates here. These are going to be conductors. Okay, and let me make that clear. Okay, so that means the electric field inside them is 0. All of the charge that we put on them is going to reside on the surface. This one on the left is going to be connected to what physicists call ground, which basically means it's at 0 volts, which basically means it's connected to some very large charge reservoir where it can basically suck electrons up or push them out to maintain that voltage of 0. The other one would be hooked up to maybe a battery or a power source, and it's going to be at some voltage. We'll say a positive V0. Okay, so just like a 2-plate capacitor, these guys have some voltage between or difference between them. I'm going to say that these guys are separated. We'll call that Z. Let me do some coordinate system here. This will be Y. And then in the X direction, they're going to be separated by a distance D in the X direction. Just make that clear. Okay. And their faces, by the way, are going to be in the X, or in the ZY plane, rather. Okay. So we want to solve for the electric field in between the plates. Okay, that's our goal. So I want to solve for E in between plates. Okay, there's no reason, if I'm right in between the plates, that the potential, let me just write that V would depend on Y or Z. So if I'm right in between the plates, I'm going to assume that the potential is only changing in between the plates. It's not changing up or down because this is at a constant potential. This is at a constant potential. If I'm right in between them, I'm going to be away from any edge effects. Okay, so if that's true, then I can just rewrite a potential that could potentially depend on the 3 directions as just a V sub X. Okay, I'm going to assume I've got some boundary conditions here based on what I've drawn. I know that the voltage at X is equal to 0 is going to be equal to 0 volts. Okay, and I also know, that's my first boundary condition. Let me number these out so we know we got 2. Okay, this is my first boundary condition. My second one, I know that the voltage at X equals D is V0, whatever that is. Okay, and I also know, since rho is equal to 0, there is no free excess charge between the plates. In between the plates, the field should satisfy Laplace's equation. Okay, so I've got a second order differential equation that's going to tell me what a general solution is, and then I've got some boundary conditions to give me a specific solution for this problem. Okay, so we already talked about what the solution is for Laplace's equation in one dimension. I know that the solution should look like the equation for a line, okay, but I still have to figure out what M and B are. Okay, but I can easily figure that out using my boundary conditions. I know, again, that the voltage at x equals 0 is equal to 0, which means that, right, this is also equal to 0. Okay, that should be easy for you guys to figure out. The B has to also be equal to 0. Okay, and then I know from my second boundary condition that V naught is equal to MD. That tells me that M must be equal to V naught over D, and that allows me to write out an equation that tells me the voltage difference between these two plates. Okay, so I get V naught divided by D times X. All right. So if I remember here, if this is my solution, my specific solution for this particular problem, this should look familiar to you guys, hopefully. Okay, we just have a potential that increases linearly between our plates. Okay, so if I have the origin at the leftmost plate here in the x direction, which is what I've already assumed, then my voltage is going to increase like this. And of course, the electric field is given by the negative gradient of this. Okay, so that is going to be equal to negative the derivative in the x direction of V, which is equal to negative V naught over D. And that tells me that I've got a constant electric field in between the plates. Okay, so if I went back and I wanted to draw that electric field here, it would be in the negative x direction because I got a negative value, and it would, so therefore it'd be pointing from this blue plate here, which is at the higher potential, assuming that that's a positive potential, to the negative plate, and it would be constant, at least in between the plates, far from the edges. Okay, so that's a good old capacitor. We should be familiar with that, okay? And we can go a little bit further with this, which is nice. That, in theory, is something you guys should know from 183. So let's go a little bit further, okay? What if, instead of knowing the potential, what if you only knew the surface charge density instead? Okay, maybe a bunch of charge was dumped onto a capacitor. You don't actually know what voltage is at, but you know the amount of charge that was deposited, and based on the geometry, you could figure out this surface charge density. Okay, well, we can start with a similar picture here. I'm going to cheat a little bit and copy and paste this here. Get rid of some of this stuff just to make it a little easier. And now I'm still going to have the leftmost plate at ground. Okay, but now I'm going to assume that a bunch of negative charge essentially left of this capacitor on the right here. And so now at that surface here, the leading surface, there's some excess positive charge, which I can define with some surface charge density rho, okay? Well, it turns out if I know rho, I can also find E, okay? So I can find electric field between the plates. Why is that true? Well, I'm going to draw a Gaussian surface here for one of these plates. I'm going to draw a Gaussian surface for the plate with our surface charge density, a little pillbox, okay? And if I think about this surface, again, if I draw that electric field, it is still going to be pointing perpendicular to my right face here. So it's going to be pointing to the left, and it's going to be still going to be constant in between these two capacitors. Inside of this conductor, I still know that the electric field has to be equal to 0. Okay, so basically, if I color this guy in here, I know that my electric field dotted with that area vector is only not 0 on this wall. Okay, and hopefully you guys all understand why that is at this point, right? At this side of all my Gaussian surfaces, on the other side of the surface of this conductor, it has to be 0 because the electric field is equal to 0. On the actual sides of my pin box, it's 0 because the area vector in that case is pointing either up or down, which is perpendicular to the direction of the electric field, and that dot product is going to give me a 0, okay? So if I want to use my Gaussian surface, okay, on that wall, I know that the magnitude of the electric field times the area of that wall is going to be equal to the charge enclosed by my little pillbox divided by epsilon naught. That tells me that the electric field is going to be equal to, right, the charge enclosed divided by the area times 1 over epsilon naught. And hopefully you guys can see that is the surface charge density divided by epsilon naught. Okay, so what this basically tells me is that if I know my surface charge density, I know E just outside my conductor. And of course, this is always true. It doesn't mean for fancy conductors, different shapes, I know what the electric field is far away from the surface, but right next to the surface, I always get this same result. Okay, so that's the magnitude of my electric field. I can be a little bit fancier. I know that the electric field is actually pointing in the negative direction in terms of drawing a coordinate system, which I can draw here quickly. Let's see, this is going to be my z direction, y is going to be along the surfaces, and x is going to point perpendicular to the surfaces. Okay, and then if I want to take this a little bit further, okay, I know that the negative gradient of the potential is equal to E. So this tells me for this one-dimensional problem, close this full derivatives, that the derivative of the potential with respect to x is equal to my E sub x. And that gives me that I know the derivative of the potential with respect to x is equal to sigma over epsilon naught. Okay. This right here is true at the right-hand surface, but since I know my general solution is a line, it's also true everywhere else, okay? So this basically tells me if I look at my general solution, okay, if I know that my derivative of the potential is equal to the surface charge density over epsilon naught, I know that that is also what m is equal to in my general solution for a potential, okay, which, by the way, right, I know the general solution. Okay, so because I know m, and in this case I still know that the voltage at x equals 0 is still equal to 0 because the way I have this set up, this left-hand plate is still grounded. Okay, so that still tells me that B is equal to 0. And now I've got a solution which tells me that the potential between these plates is sigma over epsilon naught times x. Okay, this is a specific solution for this problem. Okay, if the left plate was not at V equals 0, but at V equals V naught, then in that case, this would be the solution. So just change what that value of B was in my general solution. So this is an example. This is an example where you know the derivative and V at 1x. So essentially this is an example of knowing a mixed boundary condition where you know the slope and the actual value of what you're trying to solve for at a particular point. Our first solution here, we just knew the value itself at 2 particular points, okay? All right, but either case we get a line, which is the solution for Laplace's equation in 1 dimension, okay? So let's just summarize here with a couple of notes. Note number 1, a line is the most boring way to connect 2 points. Okay, I think we can all agree with that. Okay. In fact, that's what's always going to be true. So the solution to either Poisson's or Laplace's equation is always going to be the most boring solution, which is to say, we'll call it featureless. It is in multi-dimensions, in essence, what it's like to connect 2 points with a straight line. You're doing it in the most efficient way. Okay, you're not adding any extra bumps or wave in there. Okay, with that in mind, we need to point out that there are no mins or maxes between the boundaries, okay, for, in this case, only Laplace's equation, okay, for the solution, rather, to Laplace's equation, okay. If there was, okay, if you looked at a solution and there was a max or min, that would imply there is some charge density, okay, somewhere. Okay, so I could show the PhET sim, or you guys could open it up, but imagine how that potential contour changed near the charges. You only saw maxes and mins where there was actual charge density, where there's actual charges, right? That's, if you got a positive charge, that's like the peak of a hill of a potential, and negative charges like the bottom of a hill. In between those charges, you were just getting smooth contours. You weren't getting any peaks, okay, or minimums, okay? That would imply a charge density. So if you do find charge density, then you're not solving Laplace's equation near those charges, right? That would be Poisson's equations, okay? So that's why we know can't get any maxes or mins, which helps keeps these functions boring, like that straight line, okay? Last little thing if we know our potential is 0 at all boundaries, then V equals 0 everywhere. Essentially, you need some charge at the boundary in order to get an actual continuous non-zero function between those boundary spaces, okay? So basically, to get something, to get something interesting that's not just 0, you have to put charge somewhere. And oftentimes, like I said, when we're solving for this, for real systems, we're thinking about plates or something like that. Can't talk and write at the same time. Where we've put some kind of charge, okay, or we've raised them to some kind of voltage, and we're trying to figure out the electric field between them. So at the boundaries of this region where we're trying to find the electric field, there is charge, okay? So these are the rules, and it's kind of easy to see it in one dimension where we just solved Laplace's equation and got that straight line. It's a little bit harder to visualize in more than one dimensions, but these rules that I wrote out, they do apply for higher dimensions as well. And we'll try to show some examples when we can.